Welcome. Today we will be discussing section 3.1. Topics include unit vector, dot product, Pythagoras' generalized theorem, and skew product. For unit vectors, we have some properties that we can utilize. We know that every unit vector has a magnitude of 1. In other words, the distance that it goes is 1. We're going to use that to say that every non-zero vector can be written as some sort of unit vector. So let V be a vector with V not equal to 0. And it's a vector of 0, so that's why I'm including that little dash mark. So what can we do? Well, V can be written as R times vector U with R being greater than 0. So we have a scalar timesing this vector. Essentially, this unit vector is determining a distance or determining a direction. And then this R is determining the distance. What is this R? Well, it'll just be the magnitude of V because we're timesing it by a magnitude of 1 because that's the unit vector. So what that entails is that we could rewrite this as V divided by its magnitude is equal to a unit vector. And that's what this R is. If I just divide it by R, I'm not dividing by 0 because it's non-zero. And I'll have my vector divided by R, and my R is the distance of the magnitude of the original vector. So now we can say that let V1 be equal to R1, U1, and V2 be equal to R2, V2, or U2. So essentially, I'm just declaring that I have two vectors here, and we can say that they are the same direction. Same direction when U1 is equal to U2, and they're opposite direction when U1 is equal to negative U2. Because we have this R being greater than 0, then if they're pointing in the same direction, they're going to have the same unit vector. If they are pointing in opposite directions, then I can just have a negative unit vector and I'll point the other way. So how can I use this? Let's do an example. We're going to find the unit vector. Finding unit vectors of V1, which is equal to 3, negative 4, and V2, which is 6, negative 8, and V3, which is negative 12, 16. So The first thing is we need to find the magnitudes of each one. So magnitude of V1 is equal to, now because we didn't specify, we're using the Euclidean distance, and so we're going to take each entry, square it, add them together, then square root the entire thing. So we have the square root of 3 squared plus -4 quantity squared. That gets us 9 plus 16. That is 25. Square root of 25 is 5. So now when we look at the magnitude of our second vector, we're going to have square root of 6 squared plus -8 squared. That gets us 36 plus 64. That is 100. Square root of 100 is 10. Finally, we have magnitude of V3 is equal to, and we'll have square root of -12 squared plus 16 squared. And that is 144 plus 256. So that's 400. Square root is 20. So now when we take these to find the unit vector, we just have to divide by 5 to each component of the respective vector. So we can write this as U1 is equal to, we're going to have 1/5 times the vector 3, -4. And so we're going to rewrite this vector, distributing this 1/5 to each. We're going to have 3/5 and -4/5. And then U2, we're going to have this vector here times by the reciprocal of the magnitude. So we're going to have 1/10 times 6 -8. Distributing and reducing, we're going to get 6/10, which reduces to 3/5. -8/10, which reduces to -4/5. And finally, we can do unit vector for V3, and we have 1/20. This is -12/16. Again, we're going to distribute the 1/20 and reduce, and we're going to get -3/5 and 4/5. Though it didn't say in the question to classify, but we can do that, and we can say that U1 and U2 are same direction. And we can also say that U1 and U3 are opposite direction. And that would be a complete answer to this question. So With the unit vector, we're now introducing this concept of direction and how to quantify what vectors are pointing in the same direction. Well, now we're going to introduce the dot product. This has a piece to play with direction, and we'll see certain properties as we continue in this video. So with the dot product, we're going to have V1 be equal to X1, Y1, and we're going to have V2 be equal to X2, Y2, and we're going to define the dot product as follows. We're going to use a dot. So think of it as like a thick dot. I would use that in case you use dot as like multiplication, just to not be confusing. And so this is going to be V1 dot V2. And we're going to define this as X1 times X2 plus Y1 times Y2. So the components in the same entry position are going to be times by each other, and then we're going to add them all together. Okay, so what are some of the properties of this? For your check on learning this week, it'll be to write down the dot product and its properties. So for the dot product properties, we have symmetry. What does this mean? It means that V1 dot V2 is equal to V2 dot V1. In a sense, it's commutative, which is where we can put it either or, much like how you could do that with multiplication or addition. It's distributive. So we have V1 plus V2. And we're going to have that be times by the dot product of V3. This is the same as if we did V1 dot V3. We did that first, and then we added V2 dot V3. We could also distribute it from the other side as well. So if I have like a V1 dot V2 plus V3, we can get the same result of distributing this and getting V1 dot V2 plus V1 dot V3. So it's distributed from both the right and the left-hand side. We then have green, which is homogeneity. Which, what that is, if I have some scalar t, and I'm going to times that by V1 dot V2. So I have this being done first. I can take that out and rewrite this as t times v1 dot v2. In other words, if I have a scalar, I can attach it to one of the entries of the dot product. And this works if it was, if I attached it to v2, I could then write this as v1 dot t v2. I can move this t to either one, it doesn't matter, or I can do the dot product first and then apply the scalar of a t. Lastly, we have magnitude identity. And we have v1 time or dot product v2 is, oh, sorry. v1 dot v1 is equal to the magnitude of v1 squared. And you'll see this come up a lot when we go through more of like theorems and proofs and go, okay, if we have this, we can write down this and vice versa. Okay. So with this, this gives rise to a generalized Pythagorean theorem. So generalized Pythagoras theorem. What happens is Pythagoras theorem, it was specifically when we're in the all reals. Now we're going to be using this in regards to a more generic vector space. An intriguing thing happens is we are going to have v1 minus v2. We're going to take the magnitude of that. We're going to square it. This is going to equal v1 squared plus v2 squared, both taking the magnitudes of them. And we're going to subtract 2 times the dot product of v1 dot v2. Now, this might look a little bit weird, but when we take the magnitude identity from the properties, you can see that this is just v1 dot v1, v2 dot v2, and we're squaring them. So it looks kind of like a perfect square sort of situation. And that's, in a sense, what we're kind of doing here. That's being loose with the language, but it's interesting that we get Pythagorean's theorem, but it kind of like kicks out an additional criteria. So we can also have v1 plus v2 magnitude squared, and we get magnitude of v1 squared plus magnitude of v2 squared. And now we're going to add 2 times v1 dot v2. So again, should look similar to like a binomial, like when I have a plus b quantity squared, or a plus a minus b quantity squared. It should look pretty similar to that. All right. So now we'll also do the skew product. So the skew product is like the dot product, where we're going to come up with a mechanism. It's going to be used in more directional sort of problems. And so therefore you'll see a lot of similarities. I'll highlight them at the end of the lecture. And so we're going to first start again with V1 being equal to X1, Y1, and V2 being equal to X2, Y2. And we're going to define V1 skew, which you can think of this like a little like mountain sort of thing, but it's like representing like an angle, V2. And this is going to be equal to X1, Y2 minus X2, Y1. Okay, so what properties come out of this operation? We have anti-symmetry. Which is V1 skew V2 is equal to negative V2 skew V1. No, that negative is attached to V2. We have distribution. So we have V1 plus V2, and we're going to skew this with V3. This is the same as V1 skew V2 plus V2 skew V3. It also works with the other way. So if I wanted to distributive, let me write it out. V1 skew V2 plus V3 is equal to V1 skew V2 plus V1 skew V3. And again, that's the same as with dot product. 3, we have homogeneity. Which is that if I attach this T to a V1 and I will skew this with a V2, that is the same as T times V1 skew V2, which is also the same as if I attach this T to V2, I get V1 skew quantity T times V2. So to amend this statement here, this is attached to V2, but I could also think of this as V2 skew negative V1, which I can also think of this as negative V1 skew V2. Oh, sorry, V2 V1. So I can think of it as either one of those cases. The reason why I highlight that is just to be consistent with any other property. So with this, we get what's known as the dot skew product theorem. And what we can do for this one is, right, we're going to say that theta is the angle between V1 and V2. Okay. And we're going to say that V1 dot V2 is equal to the magnitude of V1 times the magnitude of V2 and we're going to times this by the cosine of theta. For V1 skew V2, we get the magnitude of V1 times the magnitude of V2. We're going to times this by the sine of theta. And then if either vector is 0, so if V1 or V2 equal 0, or if they both equal 0, we're going to have that V1 dot product with V2 is equal to 0, the 0 vector, and also the same with not the 0 vector, just 0. And V1 skew V2 is also 0. So if either V1 or V2 is a 0 vector, the output is 0. On the next video, we will discuss what useful properties we have, namely here's the main benefit between the skew and the dot product is that we start introducing the theta, or the angle between two vectors. Something I want to point out is that the properties are fairly similar in the sense that we have symmetry with the dot product. We have asymmetry with the skew product, meaning that we have this anti-symmetry of having to include a negative. They're both distributive from the right and the left. And for homogeneity, we can attach a scalar to one of the vectors or attach it at the end. And that's the same with all. The dot product has an additional property of the magnitude identity that if we take a vector and take the dot product with itself, that's the same as the magnitude squared. In the next video, we'll explore more concepts as well as examples. Reminder that the check on learning is to write down the dot product and its properties. Thank you for watching and have a great day.